Hello everyone. I'm Sandra DP. My registration number is 419 and we are group 61. And in this video, we are presenting a conference paper that is closely related to our final year project. Our final year project is blockchain-based defect and fraud identification in supply chain. The paper we have selected is developing an anti-counterfeit system using blockchain technology. As a research publication information, this paper was authored by Anthonya, Michael, Christian Lee, Rafaelle, Richel, Pearla, and Sebastian, Edberta. This paper was presented at the 7th International Conference on Computer Science and Computational Intelligence, which was held in Jakarta, Indonesia, in December 2022, hosted by Bina Nusantara University. It has received 24 citations, which highlights its significance in the field of blockchain applications. As an introduction, we chose this paper because it deals with a problem that is very similar to the one we are tackling in our project. Counterfeiting is a major issue in global markets, especially in industries like fashion, electronics, and pharmaceuticals. The most traditional solutions like QR codes, barcodes, or certificates can be easily forged or tampered with, making it hard to guarantee a product's authenticity or quality. This creates a serious gap in consumer and stakeholder trust, and that's where blockchain technology becomes relevant, offering transparency, immutability, and traceability. As objectives in our paper, uh, the paper sets out four clear objectives, all of which are strongly aligned with the goals of our final year project. The first objective is develop a blockchain-based anti-counterfeit system, similar to how we are designing a blockchain-based platform to detect and log product defects and fraud throughout the supply chain. The second one is enable traceability from the manufacturer to the end consumer, just like in our project, where traceability is key for identifying the exact point at which defects or fraudulent activities occur. The third one is use smart contracts for secure transactions. We also leverage smart contracts in our system to automate checks, verifications, and alerts when anomalies are detected. Evaluate performance and cost efficiency is the fourth objective. So from here onwards, this presentation continued by my friend. So thank you.
Thank you, Taruka. From here, I am going to present about methodology of the conference paper. The methodology has several aspects: theoretical background, system model, operation workflow, anti-counterfeiting and traceability, and data set. We will see one by one. First thing is theoretical background. Since it is a blockchain development related paper, blockchain is an immutable digital ledger for traceable transactions. These blocks are cryptographically linked and verified by the network consensus. Ethereum supports Turing complete smart contracts via Solidity. Smart contracts execute automatically when conditions are met. Development and testing are done using Connect personal Ethereum blockchain and Remix IDE for Solidity smart contract development. These are the theoretical backgrounds of the paper. Next, we will see about system model of the paper. As you see in the block diagram, the system model have main three parts. They are manufacturers, distributors, and consumers. We will see one by one. Manufacturer creates Genesis blocks and manufacturers input original product and shipping data. Manufacturer can trace but not update the data after post shipping. Next, we will see about the distributors. Distributor records transaction data like dates, buyer info. Distributors can trace but not view current owner addresses. It prevents cloning. And consumers can verify the trace product info, cannot modify blockchain or see owner addresses. Consumers can verify ownership through a checker function. This is about the system model as you can see in the block diagram. There are several nodes and these three main factors. Next methodology will be presented by Tayanan. Thank you.
Thank you, Vishan. Let's start with the operation workflow. This diagram illustrates the operation workflow. The process starts with the manufacturer who initializes the blockchain by creating what's called a Genesis block. This block contains the manufacturer's credential and basic setup data. Once initialized, the manufacturer can raise the product-specific information, including product ID, name, batch number, production date, shipment data, and the receiving distributor ID. This information is stored in a new product block on the blockchain. When the product is sent to a distributor or seller, the system records the transactions by updating the product's block. This step is done using a smart contract that validates the transfer and changes the ownership record from the manufacturer to the seller. Now, when a consumer is interested in buying a product, they can use a system to query the product ID and view the critical information such as the production and the shipment history. To further ensure security, the consumer can request the seller's blockchain address and verify it through a built-in verification function. If the address matches the current owner records on the blockchain, the system confirms the product legitimacy. Finally, once verified, the consumer completes the purchase and the ownership is transferred to via another smart contract. The entire workflow ensures end-to-end transparency and prevent unauthorized tampering at any stage of the supply chain. Now, let's move to the system anti-counterfeiting and traceability mechanism. These rely heavily on the core features of the blockchain technology, such as immutability, consensus, and traceability. Immutability means that once a block is added to the blockchain, the data inside it cannot be changed without altering every subsequent block, which would immediately be rejected by the network. This prevents any modifications or forgery of the product information. The consensus mechanism ensures that all participating nodes in the blockchain agree on which transactions are valid before they are added to the chain. This means only authorized and verified action can be recorded. Lastly, the system maintains excellent traceability by recording every transaction throughout the product life cycle. This prevents an unbroken, transparent records from manufacturer to the final consumer. The combination of these features ensure a high level of product security and builds trust among consumers, sellers, and manufacturers alike. Now, let's move to the dataset and simulations. The researchers validated their model using a set of dummy data. They created an Ethereum account using a Remix ID which each account preloaded with 100 ETH for testing. The simulation was done through using a role such as manufacturers, sellers, and consumers. And Harindran will continue this presentation. Thank you.
Now we have discussed about the results and discussion in the conference paper. First thing is the transaction. In the transaction, there's a three transaction. First one is the product registration. In the product registration, what we are going to do with what they have done is they input the product details, product ID, manufacturer date, and manufacturer place, and seller ID, all the things, and create a block. So when we create a block in the blockchain, that transaction cost is higher than other than the transaction cost. There's a 308,771 going. So then we move to the next transaction. That is a product transfer with manufacturer to seller. When we transfer to manufacturer to seller, we just put seller ID and the product ID. With that details, we can create that manufacturer to seller transaction. Just we input the details, not create a block. So the transaction cost is very less than previous. Then we move to the product transfer, select consumer. In this one, we just input seller ID, consumer ID, and product ID. This is about the transaction in result and discussion. Then we move to the product traceability. Here, with the seller ID and product ID and seller address, we can verify that person. Is this a verified seller for that product? Then we can input the ID of the product and get the what are the things about that product, and we can get the ownership history for that product. But we can't get the current owner address. If we get the current owner, that person, is there any person that will say, I have this current owner address and you can buy from me, but we can't buy because this owner get the address from that blockchain and say he is a current owner, but this is not a good way. So what they have done is they just get the current owner address when you buy the product, and you can verify with that address. If you input that address, that will hash, there's the same hash inside there. They verify that and tell as this owner is a verified person. So you can buy that product. That's about the product traceability. And when we consider about the cost analysis, they have done for 10 products and 10 multiple transactions, there's an average per amount for the transaction. There's a 3 transaction cost. First one is block creation. Second one is the seller to consumer. Then third one is the manufacturer to seller. You can get totally 715,000 yuan approximately. So this is equal to 0.92 USD when 2022. But current days, the Ethereum price is high. So for the future work, what they have done is you can use for the medium price products for the system. But in this system, there's an issue. Inside the system, there's a middleman is there. So we can verify that type of middleman with the GPS sensor or IoT sensor. When we integrate that IoT sensor, GPS sensor with the blockchain, we can reduce the fraud in this system. And other than that, in current days, Ethereum amount is very high. So we can use any other coins instead of that, like a Cardano or something, alternate blockchains. But we need to consider the transaction fee and then consider the transaction speed. That's it about the conclusion and future works. That's it. Thank you.